p squared for mod p squared reasons. We find integer matrices A and B such that determinant of ax minus b is f of x. Okay, so that's like our lift. Our f has been mapped into the space AB, and the map is just taking this determinant of ax minus b to get back to the polynomial. And what further properties do these A and B have? Well, if you look at the polynomial delta n of determinant of ax minus b, okay, so if you have two matrices, n by n matrices A and B, there's a natural discriminant polynomial on pairs of matrices A comma b. Namely, you take the discriminant of determinant of ax minus b. So that's a polynomial in the entries of A and B. Right? Its degree is suddenly n times more than it used to be, but it's still a polynomial in the entries of A and B. And we're going to find this lift from f to a comma b, so that even though the discriminant of f was a multiple of p squared for mod p squared reasons, if you look at it now, the discriminant polynomial on a comma b, it's the same value. It's still a multiple of p squared, but it's now happening for mod p reasons. And the way we're going to do that is we're going to take that p squared, which is arising as the determinant of b, and we're going to split the two p's, right, and put them on some kind of diagonal. So I'll actually show you what the matrices A and B are. So I'll show you in the case n equals 5, so degree 5 polynomials. So imagine you have a quintic polynomial, monic, f of x, such that the last coefficient is a multiple of p squared, second to last coefficient is a multiple of p, and we're going to lift it to an a comma b. This is going to be our a, so it's just the split quadratic form. And why is this good to take as a? Well, remember we wanted the polynomial to be monic, and the determinant of this is 1, so that's good. So if you take determinant of ax minus b, automatically this will cause it to be monic. And what do we take for b? We take that thing. And you'll notice how these p's have been split apart here. What is it? So what is the final coefficient of determinant of ax minus b? The last coefficient is just determinant of b, right? And what is the determinant of b here? Well, you see that it's just p times c5. So it's just c5 times p squared. So it's an arbitrary multiple of p squared, if you choose. So c5 is arbitrary. But notice the p's have been split into 2 there, which is useful for making the n discriminant multiple of p squared for mod p reasons. So if you work out what the determinant of ax minus b is for these two matrices A and B, you find that first of all it's monic, and then the next 3 coefficients are totally arbitrary, and then the next coefficient is p times c4, and the last coefficient is p squared times c5. So an arbitrary thing times p, and then an arbitrary p squared times arbitrary thing times p squared. So this is like the totally general form of a polynomial where the discriminant is becoming a multiple of p squared for mod p squared reasons. But the point is that if you don't view this discriminant polynomial in terms of the coefficients of the quintic, but if you view it as a polynomial in the coefficients, in the entries, the non-zero entries that you see of A and B, you check that the discriminant is actually becoming a multiple of p squared now for mod p reasons. If you change all these non-zero entries that you see by just multiples of p, the discriminant of determinant of ax minus b will still remain a multiple of p squared. It's really now happening for mod p reasons. So if we view this discriminant of determinant of ax minus b, which is just the discriminant of f, as a polynomial, not in the coefficients of f, but in those 12 variables of b. So we're actually going to always fix a to be that. So that's not even part of the variables. And we're always going to take this top 2 by 2 block of b to be 0. So we're not even going to consider those as variables. So the number of variables that remain is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 variables of b, right? That's the things above the main diagonal that are not in that top 2 by 2 block. There are 12 variables of b. And if we look at this discriminant as just a polynomial in those 12 variables of b, then it turns out that this discriminant is a multiple of p squared in these 12 coordinates for mod p reasons. Those p squared has been split into those p's, and now the discriminant is becoming a multiple of p squared for mod p reasons. Even though the discriminant has a polynomial c1 through a1 through a5 was a multiple of p squared for mod p squared reasons. Okay, but we split apart those p squareds into 2 p's. Okay, so this looks great, and it seems like now we can just apply the Ekadel sieve and we'll be done. No, because something funny happens. So we were very excited when we found this map. Suddenly mod p squared reasons had been changed to mod p reasons, and this is great. But something funny happened, which is that it is for mod p reasons, but it's still only lying on a codimension 1 variety and not codimension 2. How is that possible? I'll explain that right now. Because it seems like if something's vanishing mod p squared for mod p reasons, it has to lie on a codimension 2 variety. How could it suddenly have only been on a codimension 1 variety? Well, here's why. So, okay, first of all, let me explain what the symmetries are. This space B has 12 coordinates, and as I said, we wanted more symmetries. This space has a lot of symmetries. Let G0 be the subgroup of the orthogonal group of A, okay, that keeps the top 2 by 2 left corner of B 0. So in other words, SLN acts simultaneously on A and B because they're both quadratic forms, by multiplication on the left and multiplication by transpose on the right. But we don't want to use all of SLN because we want A to remain the split form. So the subgroup of SLN that preserves A is the orthogonal group of A. So if we have the orthogonal group of A act simultaneously on A and B, A will remain as it is because it's the orthogonal group of A, and then B will move around. But now we want to take the subgroup so that it also preserves the top 2 by 2 block. Yeah, that's some non-reductive subgroup of SOA, but it's a fairly big group. So that's going to be our group G0. And so G0 is a symmetry of this whole situation, of these kinds of shaped matrices. G0 acts on pairs A comma B, but it preserves A because it's in the orthogonal group of A, and it preserves the shape of B by definition. And of course, note that the action of G0 also preserves equation 1. In other words, determinant of AX minus B will remain that polynomial even when you act by G0, right? Because it's determinant. So if you multiply on the left and right by determinant 1 matrices, it's not going to change the determinant. So it preserves that fact that you're getting that polynomial f of x. So that's what I meant by having symmetries, that we've found two matrices such that determinant of AX minus B is f of x. So we can act on AB by this huge group and you still get lots of other such matrices. One can work out what the invariants are for this group action. The invariants for the action of G0 on this 12-dimensional representation V, well, there are 5 invariants that you see right away. C1, C2, C3, C4, C5. Those remain invariant. But if you do a dimension count, you find that that's not everything. There's one more invariant that's lurking around. So when G0 acts on this 12-dimensional representation, you do get the coefficients of f of x, but you get one other invariant. So together with one additional invariant, which we call the Q invariant. And the Q invariant, it turns out, just involves these top 6 entries of B right here. And that there's one invariant defined polynomial in these 6 entries right on top, at the top of B there, that remain invariant under this action of G0. There's that one invariant. It's degree 6 in this case. And so you might wonder, what does that invariant evaluate to? Well, so our first 5 invariants were C1, C2, C3, C4, and C5. There's one thing in the picture that we didn't use. If we evaluate Q on these pair of matrices A and B, we find that Q of AB equals P. So we've embedded the space of monic polynomials into a bigger space, where with more symmetry, such that the space of invariants are the coefficients, together with this P, has come out as an extra invariant. So what that means is that we have this invariant polynomial Q of AB, and we know that P squared divides the discriminant. In general, what happens here, as polynomials, Q of AB squared divides the discriminant of A comma B. So even though the discriminant on monic polynomials is an irreducible polynomial, when we've done this lift to the space AB, it's actually become a reducible polynomial, and a square factor has come out, discriminant of A comma B, and that's what we made equal to P. And because it's a square factor, just think about this: if you have a polynomial and it has a square factor, then that can become a multiple of P squared for mod P reasons, but still lie on a codimension 1 variety because it's a square factor. It's just that one factor that has to vanish to cause P squared to divide the discriminant. So that's why the Ekadel sieve doesn't just apply, because when we mapped it to this bigger space, that p squared is happening because of QAB vanishing and nothing else vanishing, because QAB squared is dividing the discriminant. Okay, so we did change mod p squared reasons to mod p reasons, but we only got the codimension one thing. So that's why Ekadel doesn't just apply in this case. Although in other cases, and other polynomials that we've handled, that did happen, and when we were done. So that's how we've handled other square-free polynomials. But this one was additionally exciting because the lifts that we always found always had this property for polynomial discriminant. Okay, so how do we handle it? Well, okay, so q of ab squared divides the discriminant of a comma b as a polynomial, even though as a polynomial it was irreducible in the coefficients of f. Okay, well, we can't apply Ekadel, but just note that it now suffices to count orbits of G0 of z on integer points of this 12-dimensional representation, satisfying height of AB, which is just defined as the height of the polynomial, less than x, such that the Q invariant, this last invariant that we haven't used yet, is larger than m. Because remember, for our uniformity estimate, to do the square-free sieve, we just need to know how often p squared divides the discriminant for large p, so p bigger than m. But all such points we've now mapped into this bigger space, and not just mapped into the bigger space, but mapped into orbits of the bigger space, because remember, orbits still had those same invariants. So we've taken monic polynomials, whose discriminant is a multiple of p squared for mod p squared reasons, and mapped them into this bigger space so that the first 5 invariants remain the same, and then you have a 6th invariant, which is that p. And we want that p to be bigger than m. So we reduced it to an orbit counting problem. We have a representation of a group, and we want to know how many integer orbits are there, having bounded height and having invariants in certain ranges. And this is where the techniques that we've been developing to count orbits with invariants in given ranges, we can just apply to this problem. So we want the height, in other words, the height of C1 through C5 to be at most x, but we also want this last invariant to be bigger than m. And our methods allow us to count orbits with invariants in given